All right, let's start again. I did notice a typo up here. Not for this rods. For thin rods. Okay. Sometimes it might be like my hand doesn't know what my brain is telling it to do. All right, second half of class, we're going back to parametric curves in the context of polar coordinates. So in this situation where we have the polar grid, and in last class period I graphed the function in a polar grid, r equals f of theta equals theta. There was this graph. And we wanted to find the arc length for that graph. We wanted to find the distance traveled if we thought of it as a motion. And you can, in fact, think of it as a motion if you like. You manipulate here. I can make the right-hand endpoint of the theta interval be b. And let b go from just barely bigger than 0 up to 4 pi. If I want to see the entire graph the whole time, like in this window, I better do plot range. I can do it outside the polar plot, but inside the show. If I do a 40, that should then go negative 40 to 40 in both directions. Ignore the outer bluish line there. Focus on the graph that you're going to see moving here. There we go. There's my spiral, according to that equation, r equals theta. If you look at it carefully, it should seem like the angle is moving at a constant rate. In fact, that's true. Theta is moving, changing at a constant rate. But the object as a motion is speeding up. So if I think of theta as being time, which if I want to, I can. So in my mind, I'm imagining it being both the angle and time going by, as this animation demonstrates. It is moving faster and faster. So the speed as a function of time is increasing. And essentially, even though the angle is changing at a constant rate, it's speeding up because it's getting further and further away from the origin. R keeps increasing. The formula for the speed I wrote down last time. Speed of the curve as a function of theta is the same formula as usual, except you got to realize that your x and y equations as functions of theta are not f of theta and g of theta. It's f of theta cos theta and f of theta sine theta. Now you could give those functions new names. Maybe I'll call this one g of theta and this one h of theta. When you do this, these are parametric equations in theta that you can now use the formulas we already knew. We can find the speed as a function of theta by doing square root not of f prime squared plus g prime squared, but instead g prime squared plus h prime squared. Actually, let's do the general case first before we consider specific examples. That's the derivative with respect to theta of f of theta cos theta, lots of parentheses here, squared, plus the derivative with respect to theta of f of theta sine theta squared. And for each of those, I've got to use the product rule when I differentiate. Look at this one first. F of theta is the first function, cos theta is the second. The derivative of the first will be f prime theta, and I have a cos theta, plus the first times the derivative of the second, and the derivative of cos theta will be negative sine theta, so I get minus f of theta sine theta. I've got to square that. that derivative. And then add the square of this derivative. I once again use the product rule. The derivative of sine is cosine, and so I get a plus sign in there this time. Now multiply this out. Is it okay to save some writing if I don't put the thetas in there? Otherwise, my arm might fall off. Okay, there's a lot of writing to do here. You gotta be careful that you don't misunderstand what I'm about to write here. I gotta FOIL each of these things. I think I'll write f prime squared c squared, where f prime is f prime of theta and c is cos theta. You okay with this? Outside times outside and inside times inside is going to be the product of these two, and there's two of them. You're going to get a minus 2f f prime cs. F is f of theta, f prime is f prime of theta, c is cos theta, s is sine theta. Plus, square this thing, I get f squared s squared. Then here, square this, I get f prime squared s squared plus 2f f prime cs plus f squared c squared. Zoom in on that if you need to. This cancels with that. Group together the two terms that involve the f prime, and you'll be able to factor it out, the f prime squared, I should say. That comes from this term and that term. And then there's two other terms that involve f instead of f prime, this one and this one. I guess I don't need parentheses there, but I put them anyway. And this is one, and this is one, so this simplifies to, now I'll put the theta back in. And I'll rearrange f of theta squared plus f prime of theta squared. So, the speed formula in this context, if you imagine theta as being the same as time, again, which you can do if you want, in a certain situation, if you like to do that, simplifies to this. I don't need to involve g and h. I can just use f. That's nice. So you had a couple of problems on the assignment. One of which was the function f was theta squared. That's going to spiral as theta increases as well, but the distance to the origin is going to get bigger a lot faster. It's going to stay pretty close when theta is real small, but it'll get pretty big real fast, though the angle still changes at a constant rate. So in that case, what's f prime of theta? 2 theta. All of this, I was thinking this integral came out nicer. Oh, it's not going to be super nice. Let's see what happens. The speed is a function of theta. Using this formula is going to be theta, the square root of theta to the fourth plus this thing squared is 4 theta squared. I guess it doesn't turn out too bad because you can factor out a theta squared like this. And then you can separate that into 2 square roots like this. And then, technically speaking, this is the absolute value of theta right here. But theta is greater than or equal to 0. And so we can get rid of the absolute value signs. So this simplifies to theta square root of theta squared plus 4 as being the thing you integrate now to find the distance traveled, to find the arc length. right? I just wrote the speed equation on here, but you integrate the speed to find the distance traveled, which is the same as arc length. So now if you want to integrate this from 0 to 4 pi, it's not the exact same as the graph that I showed on the screen because it's a theta squared there instead of a theta. It's actually an integral that's not too hard to do. This is good practice. Let's go ahead and do it here. Do a substitution. And let's go ahead and practice changing the limits of integration too. Let's let w equal theta squared plus 4. dw will be 2 theta d theta. That means theta d theta will be 1/2 dw. If you're going to write a new definite integral involving the new variable, you must change the limits of integration. This is something you should know for the test. Change those limits of integration. When theta is 0, w is 4. That's the new lower limit. When theta is 4 pi, this is not real pleasant, but I guess you get 16 pi squared plus 4 for the upper limit. And you've got a 1/2 dw and a square root of w in here. W to the 1/2 and a 1/2 dw. That'll be the integral to do to get the answer. Not super pleasant, but doable. You get w to the 3/2, divide by 3/2, which is the same as multiplying by 2/3. Looks to me like you're going to get a 1/3 w to the 3/2. Don't go back to theta here. Keep it in terms of w. 1/3 16 pi squared plus 4 to the 3/2 minus 1/3 times 4 to the 3/2. 4 to the 3/2 is 8. So it looks like minus 8/3. So 4 here. Does that look good to people? Do you see any mistakes at all? I haven't created any mistake or something. Let's see what Mathematica gives for this. Let's see. Integrate 0 to 4 pi. I'll do the original integral. Theta. I can do escape, th escape to make a theta. You don't have to use theta, but it doesn't hurt. Square root. What is it? Theta squared plus 4. Sorry, this is kind of a mess. There. Looking over that integral. Theta squared plus 4. Looks like I might be right. Let's see. Let's try expanding this. Except instead of a 16, they have a 4. Maybe they factor out. They might have factored out a 4. Yeah, factor 4 out of this. 4 to the 3/2 is 8. You get an 8/3 there and a pi squared, 4 pi squared plus 1 inside. So it looks like I did it right. These are the same answers. What is that? Let's try to guess what it is. Let's go back up here and do into our manipulate and change the theta to a theta squared. Though we might need to make our plot range bigger to see the whole thing. Now, yeah, we're going to have to make our plot range a lot bigger, in fact. Let's see, 4 pi is about, what, 12 point something? 13 squared is 169. We should go out at least to 169, say 170 here. Oh, and the polar grid is not big enough. Okay, whatever. Even labels the polar grid. How about that? It's the length of that thing. I don't know, 500 or 600 maybe? As a wild guess. Between 600 and 700. Okay. That's the length of that. Distance traveled or arc length. But you can do more than just find arc length. I guess here's the last new formula before the test. though you did read about this formula if you did the reading, you can find the area swept out by the curve. And this is where I'm going to bring vectors back into play. Let's go back to the original example. Just a theta instead of a theta squared. Make our plot range back to 40 here. So here's our curve. I'd like to put position vectors on this, and a velocity vector too, but first let's focus on just the position vector. You don't need to know how to create position vectors in Mathematica or velocity vectors for the moment at least, maybe later in the semester. But you should know the idea. Really all we've talked about so far is the visual idea. I mean, I did a little bit of algebra on the board with I hat and J hat, which is also in Appendix D, but we haven't really had time to go into that in depth. So we're just thinking of vectors as being arrows. They have a certain direction, a certain length. You put the base of the arrow wherever you want to make the most sense out of it. With a position vector, you want to put the base, the start of the arrow, at the origin, and it points toward the curve as it moves. It's like it's a pen tracing out the curve, which probably means I should make it red, a red arrow. And the velocity vector, it's best to put that to be located at the object itself and to move with the object. Graphics and arrow are what we use to make these vectors. Actually, to be more consistent in my coloring scheme with things, I should probably make the curve blue and the position vector blue. So I'll change this to blue and make the velocity vector red. Let's make the position vector first. Make it with graphics and arrow. Put the position vector at the origin. This is going to start it at the origin here. Where do I want to end it? I want to end it at the location of the object as it moves. At those x and y coordinates right there. I got to use the conversion equations. X equals r cos theta, y equals r sine theta, because graphics assumes you're in rectangular coordinates, not polar coordinates. So I have to put those things in here inside curly braces. Theta times cos theta, because f of theta is theta here. And theta times sine theta, though actually, I know I'm making a mistake here actually. I need to use a b instead of a theta because b is the animation parameter. But b is theta, essentially. Now we see an arrow, which initially is not drawn so nicely, it's because it's at the origin. But then, after a certain amount of time, once you get far enough away from the origin, then it looks better. There's your position vector. It's kind of like a pen tracing out the curve as it goes. You should know that's what a position vector is. What about the velocity vector? Let's make that red. You don't want to put the base of the velocity vector at the origin. Okay? You don't want to do that. You want to put it at the location of the object as it moves. So I want to use this as essentially the starting point for the velocity vector. Oh, let's see here. We're going to have to differentiate this thing, though. I wonder what the most efficient way to do this. I think the more efficient way to do this would be to do this. Kind of like in my videos about parametric curves, define a new function, c of b. Let me just copy and paste this up here. And instead of having this stuff, I'll just put a c of b. Because then, here I can put c of b, and then c of b plus c prime of b. Now it's really the c prime that's the velocity vector itself, not c of b. But this, putting this first, makes the velocity vector be based at the location of the object as it moves. And taking that and adding the derivative makes it go to the right. direction and have the right length. It makes the end point of the arrow be at the right spot. I'm not explaining that really. But the thing you should know about the velocity vector is it's always tangent to the curve. It points in the direction of motion at any instant of time, the instantaneous direction of motion. And its length equals the speed action. You can see it's getting longer as you go, because the object is speeding up. And if we can find a formula for the speed, we can integrate it to find the distance traveled. In fact, we already did that except for the other example. But the blue vector, the position vector, also sweeps out area as theta increases. It sweeps out area. There's not an area under this graph, but there's an area swept out by the blue vector. That area swept out can be calculated pretty easily, actually. The formula is to integrate area swept out. Formula is to integrate 1/2 times f of theta squared d theta as theta varies over the range it's varying over. Actually, in most books, I typically see them use alpha for the lower limit of integration and beta for the upper limit. For us, this is going to be 0 and 4 pi, and f of theta, if it's this example on the screen right now, f of theta is theta. You get a theta squared here. If it's the other example, f of theta was theta squared, then you get a theta to the 4th. So this is a pretty easy integral to do. 1/6 theta cubed from 0 to 4 pi. 4 cubed is 64 pi cubed over 6, it looks like. Rewrite that to you, easier to see. 64 pi cubed over 6, or 32 pi cubed over 3 is the area that's swept out by the blue vector as you go from 0 to 4 pi. Pi cubed is going to be around 30. 32 times that's going to be 900 or so, a bit bigger. Divided by 3, we're going to be a bit bigger than 300 square units for the area swept out. Now it's going around and around, so it's like its areas get double counted because of that. I mean, so if you try to compare it like with an area of a disk about this big, you got to realize you're double counting areas that have already been swept out. I think I better not try to approximate it. Well, that's going to be a bit bigger than 300 square units is what you get. And the formula is pretty simple, not too hard to use. Let's end class by trying to intuitively see where that formula comes from. In terms of differentials, infinitesimals, in general, if you've got some polar curve that's graphed using polar coordinates, maybe it looks like this, as theta varies from alpha to some other angle beta, what's the area of that thing? That would be the area swept out as theta varies, position vector of the object as it moves. If you think in terms of slicing, you can derive the formula, but you have to be careful with this kind of slicing because it's in polar coordinates. You have to slice along radial lines away from the origin. And so your slices, even when they're really thin, technically are somehow, well, they're thicker at the end than they are at the origin. But if you imagine infinitesimally, to have an infinitesimal angle there, d theta, at the end of that, even though it's not an arc of a circle, if theta is really small, it would be approximately an arc of a circle. And so you want to find the infinitesimal area of this arc. How do you find the area of an arc of a circle? Circle of radius r, you know, has area pi r squared. Capital R is the radius of a circle, say. The area of the circle is pi r squared, which can be thought of as 1/2 times 2 pi times r squared. Why am I doing that? Because 2 pi is one rotation. An arc of a circle is just a piece of a circle. If it's got angle theta, essentially it's the same formula except replace the 2 pi with a theta. The area of this blue region here, if I shade it blue, is 1/2 theta times r squared.
Where do we get the 1/2 from?
From noticing that pi is the same as 1/2 times 2 pi, and realizing 2 pi is the entire way around the circle in radians, the idea is this formula generalizes to this one for other radian angles. So if we go halfway around the circle, for example, theta is pi, this becomes pi over 2, half of that. And area of a semicircle is half the area of the circle. So because of that, this formula should make intuitive sense. And if you apply this formula now, with this distance being f of theta, which is really the same as capital R in that formula, dA should then be 1/2 f of theta squared, let's see, that's R. 1/2 f of theta squared d theta. Yeah. Compare it with this thing. Got the 1/2. F of theta is what R is, and that's why that's being squared. And the d theta is like the theta there. And look at that. That's exactly what we integrate over here. Add those up to get the total area swept out. Again, this is not an area under a graph. It's an area swept out by a position vector of an object moving along a polar curve, treating the angle as if it were time, which is what we are doing. Actually, you don't have to think of it that way to get the answer here, but that's what we've been imagining. Okay, on Wednesday we're putting everything together, trying to make it a cohesive whole, and reviewing for the test at the same time. So I'm ready to do that. See you then.